assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So for part A, the energy at the turning point is all kinetic. So this would be the total amount of energy at the turning point would be equal to 1/2 times the spring constant times the maximum displacement squared, where this is equaling 1.00 joules, and we know that x, the maximum displacement, is equaling 0.100 meters. Therefore, the spring constant can be solved, and this would equal 2 times the total potential energy, or the maximum amount of energy, divided by the maximum displacement squared. This is equaling 2 times 1.00 joules divided by 0.100 meters, quantity squared. This is equaling 200 newtons per meter. For part B, this would be your answer for part A. For part B, the energy as the block passes through the equilibrium position would be purely kinetic. So we can solve for the mass. We know that the maximum velocity, the maximum speed, would be 1.20 meters per second. And so we can say that the energy here would be equal to 1/2 mv squared. And so m would be equal to 2 times the total amount of energy divided by the maximum speed squared. And so we can say that the mass would be equal to 2 times 1.00 joules. This would be divided by 1.20 meters per second, quantity squared, and the mass is 1.39 kilograms. This would be our final answer for part B. For part C, we're going to use equation 1512, and then we're going to divide by 2 pi. And so we find that the frequency is going to be equal to 1 over 2 pi multiplied by the spring constant divided by the mass. This would be equal to 1 over 2 pi multiplied by the square root of 200 newtons per meter, the spring constant that we found in part A, divided by 1.39 kilograms, the mass we found in part B, and we find that the frequency of the oscillations is going to be equal to 1.91 hertz. This would be our answer for part C. That is the end of the solution. Thank you for watching.